Welcome again to the second day of the Carnot Battery webinar. So it's wonderful you can join us today, and welcome back again if you joined yesterday as well. So once again, my name is Adriano Sciacovelli from the University of Birmingham, and I will chair this webinar that is co-organized by a few colleagues from the IEA Energy Storage Task 36, DLR in Germany, the UK Supergen Energy Storage Network Plus, and the University of Birmingham Center for Energy Storage. So Angela, the project manager for the Supergen Network Plus, is here, and you might have been in touch with her a few times for the organization of the event. So thanks again, Angela, for your help. So just a few words before we actually dive straight away in the presentations also for today. So we have hopefully a rich agenda also today, with a mix of talks between academics experts and industrial experts on Carnot batteries and on hardware and components around the concept of Carnot batteries. So once again, I have just some general points for you. So we start in the right order. So you will have obviously opportunities for asking questions according to the time slots in the agenda. You can ask questions in two ways. So you can either drop your questions in the chat box at the bottom of the Zoom facilities. Please feel free to do so at any point in time. And during the Q&A sessions, I will read out aloud your questions to the speakers. You also have another option, which is to raise your hand, again using the facilities, Zoom facilities at the bottom, so you can then unmute yourself and ask questions directly to the speakers. So once again, I need to tell you that Angela is recording this webinar, and we very much hope we can take for granted the permission to do so. If that's not the case, obviously, please contact Angela, and we will have a discussion about what to omit from the recordings. So without further ado, we can actually dive straight away into the first presentation, since some of you and most of you have been here also yesterday. So you have been already informed about the framework of the Supergen Energy Storage Network Plus and the Task 36 from IEA. So we will have a little bit more time for question and answers after the first two presentations. So I would like therefore to bring in Johnny Cochrane from Highview Power. Johnny, if you are there, please, the floor is yours, and please go ahead and share your presentation. We are looking forward to hear more about liquid energy storage and Highview Power.
Thanks, Adriano. So can everyone see my screen?
Yes, if you can go in presentation mode, would be great. Thank you.
Perfect. Brilliant. All right. Morning, everyone. So my name is Johnny Cochrane, and I'm the Process Engineering Manager at Highview Power. So we've been asked to give a brief presentation to you today, and we're going to cover a number of topics. There's quite a lot to talk about. So I want to start off by talking about Highview's history a little bit, and the design, our current design process cycle, the high-level basics of how it works. And then the main thrust of the latter part of the presentation is to talk about our demonstrator plant, give you an overview of what happened there and any lessons learned. So if I skim over some stuff a little bit too fast, or you didn't pick up what I was saying, please ask a question and I'll try and answer it in the Q&A session. So the very basics, like any energy storage system, LACE is composed of a charging system, a storage system, and a discharge system. Our charging system is an air liquefier, akin to what you might find in the industrial gases industry for air separation. Our discharge system is akin to the Rankine cycle you'd find in a steam plant. Our working fluid is liquid air, and we don't have a condenser stage of our plant. We simply vent the dry air out to atmosphere, so hence the open Rankine cycle. And finally, we've 4 types of storage.
Hallo, grüß dich. Hallo, danke für den Rückruf. Bitte gerne. Hab gerade eben eine E-Mail bekommen. Ja.
Sorry. So we have 4 types of energy storage. We have the main form of energy storage are liquid air vessels. These are cryogenically insulated pressure vessels, which store the liquid product from the liquefaction process, which is our working fluid for our power recovery system or our discharge system. We also have 2 forms of thermal energy storage, hot thermal energy storage. This is the heat of compression, which we take off our compression trains. So we have hot thermal energy storage, which is about 400 degrees worth of sensible energy, which we capture in molten salts tanks. We also have what we call our low temperature thermal energy storage, which is capturing thermal energy in about 200 degrees Celsius or so. And finally, this is in a pressure vessel of a mixture of water and glycol. And then finally, we have our 4th form of energy storage, which is what we call our high-grade cold store, a pressure vessel filled with gravel. And we use a heat transfer fluid of dry pressurized air. And this imparts cold or stores cold or discharges the system of cold for liquefaction and power recovery. So that's just a high level of the main systems. Here we have a bit of another high level sort of process diagram showing the energy flows. So on the left-hand side, roughly, we have our charging system, our liquefaction. In the middle, we have the storage. And on the right-hand side, we have our power recovery, our discharge. So in principle, the liquefaction system works by taking in ambient air and compressing it across 2 compression trains, first to about 17 bar or so, and then further to sort of up to 60 bar. We, insofar as possible, adiabatically compress the gas, and this leads to high temperatures at the exhaust. And this is valuable energy, which we store and then impart to our heat engine during the discharge. So when we've compressed our gas to 60 bar and we've removed the thermal energy from it, we put it across our liquefaction system, or what we have here denoted as refrigeration. So we have a cold box, which comprises a number of cryogenic process equipment, and we cool the gas down in what we call a main heat exchanger, which is a brazed aluminium plate heat exchanger. We cool the gas down from about 20 degrees down to minus 150 degrees Celsius. And then we throttle it across a Joule-Thomson valve, which is a valve with a very large pressure drop, a very large restriction. And the gas goes from being supercritical pressure to subcritical pressure and drops into the saturation dome. It turns into a two-phase fluid, I should say. And the liquid is drawn off in a separation vessel and pumped into our liquid storage system. We also, our refrigeration, our liquefier system is loosely based on the Claude cycle, which means that a portion of our refrigeration is provided for by cryogenic expander. So during the cooling process, we take off a portion of our gas, which is again at 60 bar. We expand it to in and around 15 to 20 bar, and we can produce some work by this, which we can use to offset the loads on the compressors. This is hooked up by an asynchronous generator. The cryogenic expander is a single stage radial turbine, and its primary function is to provide this refrigeration effect. So the gas is cooled down to about minus 160 degrees Celsius or so, and it's run against the process gas in the main heat exchanger, and this provides about 50% of the cooling requirement. So our second form of energy storage is our high-grade cold store, which I mentioned is a pressure vessel filled with gravel. This provides our low temperature thermal sink for the liquefier and provides an excess 50% of the refrigeration requirements. And this system, I'll come on to it now in the power recovery, but this system is charged with cold, if you like, or the thermal sink, the low-grade thermal sink is created during the discharge process. The heat of compression, as I said, is stored in 2 forms of thermal storage. We store the hottest in molten salts, and we store the 200 degrees in a pressurized water glycol system. On the discharge side, we have our power recovery system. We pump up our liquid air in a multi-stage centrifugal pump, or a number of them, to about 150 bar. We run it across, we turn the liquid into a gas by running it across a heat exchanger, which we call an evaporator. This should be probably called vaporization more than anything else. But as it heats from -150 to about 20 degrees Celsius, we take off that valuable cold sensible energy, and that's what's stored in our low temperature thermal sink. We continue to reintroduce heat into our gas, and we run it across a 4-stage axial steam derivative turbine, and we produce mechanical power, which is sent to a generator to send electrical power to the grid. So just a very brief overview of our history. We started off in around 2005 in a garage, and then made our way to Leeds University, where a lot of analysis was done on this. And then we moved on to our pilot plant, which we built in West London, in Slough near Heathrow. This was commissioned in 2011. 350 kilowatt discharge power system. I think it's about 1.5 megawatt hours. We ran this for a number of years and validated our process at a substantial scale, so we could prove, we can recover all of this energy and create power with it. So this was then finally decommissioned and donated to the University of Birmingham, where it currently lives. Moving on from this, we built a demonstration plant in the Greater Manchester area in Pilsworth, outside Bury. I'm going to talk about this in a lot more detail, so I'm not going to dwell on it. And finally, we have the current plants, which we're working on at the moment in the US and in the UK. And these are much larger scale. So we've got a 50 megawatt discharge with a 25 to 30 megawatt liquefier input, and then about 300 megawatt hours. So in the case of the UK, this would be about 6 hours worth of storage. It tends to be a lot higher for the US markets. This is just a blown up picture of what you saw on the previous slide. And this kind of gives you a sense of scale. So you can see we have a lot of vessels which dominate the landscape. Over here on the left-hand side, we have our high-grade cold store vessels, and filled with gravel, using dry air as the heat transfer medium. Behind them, we have our liquid air vessels. Behind them, we've got our glycol water pressure vessels, and there's some supporting equipment behind them, which is a pressurization unit and a nitrogen generator for blanketing. What can't be seen here is our molten salt tanks, which are actually at a lower height of around 10 meters. So they can't really be seen in the background. And we also have 2 kiosks here. On the left-hand side, behind all those vessels, we have our turbine hall, which has our generator and our expansion turbines. And on the right-hand side, we have the kiosk with our compression trains for our motor and 8-stage centrifugal integrally geared compressor. So moving on to sort of the main focus of this presentation, which is the Pilsworth demonstration plant. I'd just like to share with you some of what happened here. So we received a grant from the government for about £8 million from, initially it was the Department of Energy and Climate Change, which is now obviously changed to the Department of Business and Energy and Industrial Strategy. So they provided about 8 million for us to build a plant. So we had enough money to build our storage facility and the discharge plant, which was important to us to prove how this could really be used to make most of the revenue services which are on the discharge side, and also to prove the supply chain, prove that we can take off-the-shelf kit and just plug and play it into our system, and there's no sort of R&D required, and it's all well-established, mature technology. So this plant was co-located. The grant was done with Viridor, the waste management company, and we used one of their sites in Pilsworth in Bury, and this site was next to a landfill. So this was a waste treatment facility, and they treated the waste, but they also had landfill gas, which they used in heat engines, and the heat engines produced electrical energy. So we were able to avail of the heat from their gas engines, and we took the heat off of their jacket, the water jackets, and we got this heat at about 80 to 90 degrees Celsius. So this was our heat source for our discharge plant. We bought in liquid nitrogen from BOC to store the working fluid for the power recovery system. So this was operational since June 2018, And it was primarily, we used an aggregator called Kiwi Power, and with them, we provided services to the grid, such as short-term operating reserve and triad avoidance, both of which I think are being phased out at the moment. So, and finally, which I'll come on to in more detail, is we built a hybrid system for enhanced response, which involved, among other things, flywheels and ultracapacitors, but I will come on to that momentarily. So we have an overview here of the plant. It was a 5 megawatt electrical output. It had a 15 megawatt hour electricity capacity. So at nominal power, we've got about 3 hours worth of storage. As I said before, we were co-located with approximately 80 degrees Celsius of heat. We used a GE, now Baker Hughes, radial turbine from Italy, which was a 4-stage radial turbine with 3 reheats. We subsequently got another grant from the government to build our high-grade cold store test cell. So this wasn't in the initial plan, but this was a very, very valuable test cell which we built and filled with sensors. So here it is here on the right-hand side, and you can see it's got plenty of thermal probes there to get a good resolution on how it charges and discharges. Just incidentally, there's the liquid storage vessels, liquid nitrogen vessels in this case, cryogenic pump, and I'll go over the rest of it in the next slide. So we got another grant subsequent to that, and we built a frequency response system which comprised a load bank for overfrequency and a Siemens MCC which worked with ultracapacitors and flywheels to provide under-frequency response. And the brains of the operation is a PLC PCS7 Siemens. So this is the slide you saw before, a few little modifications. This is the storage and discharging system, which was built at Pillsworth, and we took the heat from landfill gas engines for our water glycol system, and then we delivered liquid nitrogen into our vessels when we were required. And all of this was sent to a data acquisition system to get as much information about the system as possible. And as usual, we ran the heat engine to provide electrical power. So just very briefly, I'm going to talk through our process flow diagram. So here we have our liquid nitrogen storage vessels, about 250 meter cubed worth. And this is at a pressure of about 10 bar and minus 170 degrees Celsius. We pressurized it to about 120 bar, which induces a small temperature increase. So it came at about minus 160 degrees Celsius. And then we have to vaporize the gas. And it first goes through an evaporator heat exchanger here, which is a printed circuit heat exchanger actually supplied by Heatrick. I think Megan are on this conference as well. So they provided the evaporator heat exchanger, which was a really robust compact solution, which allowed us to capture, this is quite a large temperature change from, this point isn't shown, but it's about 10 degrees Celsius. So there's a huge pseudo-latent phase change occurring here, and there's a lot of cold energy, which we could then subsequently store in our high-grade cold store test cell. So we heat the gas to about 0-10 degrees Celsius here, and it's further heated in the first heater from the water glycol 80 degree, 90 degree heat that we've captured. And this then goes through the first stage of our radial turbine, where it's expanded to an intermediate pressure. It's reheated, expanded, reheated, expanded, reheated, expanded. So each stage is approximately 80 to 90 degrees Celsius, depending on the temperature of the heat. It comes out at about 1.2 bar here or so, and it then subsequently has to go through 2 more heat exchangers. So the first is to heat it up again to about 80 degrees Celsius. This is necessary to provide enough driving force for this evaporator heat exchanger. And then finally, this comes out quite cold, and this cold front can be captured in the high-grade cold store vessel for data analysis. And this heat is being supplied at 88 degrees Celsius at a pressure of about 2.5 bar gauge. On the thermal store side, we have about 88 degrees worth of heat and a lower bound temperature of 32 degrees Celsius resulting from the heat engine. So we took the heat from our heat engines here. This is, for some reason, this is drawn a bit strangely, but heat engine 1 and 2, 3, and 4 here. and we took the heat and returned it to our thermal storage vessels. When we were required to send heat to our heat engine, we'd simply run our supply pump. So this is a horrible slide, and apologies, but this is kind of it's good. It's a useful to see how the layout of the plant looks. It's all a bit busy though. So as I mentioned before, we were co-located. We were on a Viridor site. So there's a lot of buildings and structures here which don't pertain exactly to our system, but this is a leachate tank which was involved in Viridor's waste management, and we have a number of administrative buildings here. And then in this area we had a lot of heat engines. And so over here were heat engines as well, but these were the heat engines we availed of for our jacket water heat for our heat engine. So we have some supply return headers here, which captured the heat and imparted it to our stratified tanks, storing the heat in the water glycol mixture. When required, pumps sent the water glycol across the pipe bridge. This is a throughway here, so across a pipe bridge at height to the main area of our plant. So here we have our Lin storage vessels, which were storing the liquid nitrogen at 10 bar. We have a cryogenic pump here, which pumped it to the right pressure of 120 bar at nominal design point. Then we had our turbine hall here, which comprises of a generator coupled to a 4-stage radial turbine. So outside we have our lube oil skid, providing lube for the bearings. We have an MCC kiosk, which has our PLC and our MCCs, and this is connected to a medium voltage cabin with switchgear. And then this was sent to a transformer to a DNO to be sent out to the distribution system. And finally, there are a number of heat exchanger skids here. So these heat exchanger skids were mostly plate heat exchangers. So we had a number of them on various piping skids. And the red pipes here are all of the pipes connecting to the turbine in and out flows to recover the heat. And over here is our printed circuit heat exchanger, which we used for the evaporation process. So this is just a little startup sequence I wanted to run past you to give you an idea of how the plant would start. So it's quite a busy slide, so it's heavily annotated. But on the bottom here, we've got the turbine speed, we've got the net power output, we've got variable inlet guide vanes, and we've got the cryopump speed. So initially how the plant starts is you open your variable inlet guide vanes to a nominal position. So I think it was about 30% or 40%. And then you ramp up the cryopump to a minimum flow set point. The variable inlet guide vanes close, and they're then controlling to ramp up the speed of the turbine to about 300 RPM. Now we had to remain in this idle speed here. This was a protocol of GE's control system, and this is something that we've since worked with OEMs to remove from subsequent plants. But this is basically their protocol stated that you had to sit at a nominal speed of about 300 RPM for a certain amount of time. And then once you got the AOK from the control system, you could move on to the next phase, which is the speed ramp to nominal RPM. So once this phase had finished, the variable inlet guide vanes opened. Again, the pump is still at minimum speed set point, so about 20 hertz or so. The variable inlet guide vanes open and the turbine ramps up to nominally 1500 RPM. Once at this point, we can enter synchronization. The variable inlet guide vanes are using precision control to allow the control system working with the generator to synchronize to the grid, so matching frequency and then phase and voltage. Once that occurs, we pull in the breakers and we're synchronized to the grid. And at this point, we can move from minimum power control and a power ramp. So we start ramping up the turbine now to a higher set point. Sorry, the cryopump, I should say. We start ramping up the cryopump speed to a higher set point, and this puts net load into the grid. And then we ramp up both the IGVs and the cryopump speed to provide a higher net output onto the grid. And this, in this particular scenario here, is about 1 meg, and this will keep ticking away as long until we get the signal to stop, or we decide to stop, or we run out of fuel. So I just want to run through the Pillsbury hybridization. So this was the last grant we got to build a very clever piece of kit, which is a number of sort of enhancements to our system. So one is just a way in which we ran our turbine and generator. SpinGen is a name we've robbed from the power and from the pumped hydro power industry. where you basically motor your generator. So you absorb power from the grid to be motoring, and this allows you to motor your turbine. The benefit of this is that a number of the steps that we had to undertake here for synchronization can be bypassed because we already are synchronized. So we simply just have to use our cryopump and our inlet guide vanes to load the turbine to nominal load or whatever our set point is. We then built a 2 megawatt load bank here, which can be seen in the foreground here, which is a heat exchanger with a heating element. And this can be used to take load locally off our turbine output or from the local distribution system. And this was connected to our water glycol system and allowed us to basically dissipate the heat into the wider thermal storage system. We also built in this kiosk here, we had a Siemens package of ultracapacitors and flywheels, and these allows us to put an extra load onto the system to shape our output. So the benefits of all this are near instantaneous import response, near instantaneous export response, and reduced turbine startup. So this is kind of a graph to show you sort of what we were trying to do with this hybrid dynamic system. So your orange graph here is, or orange trend rather, here is the system motoring in spin gen mode. So you can see we're at a negative load of about minus 300 kilowatts, and we're motoring along, absorbing power from the grid in a kind of a readiness state. We get called to operate and we ramp up the turbine to nominal power. So we overshoot and then we settle down at the two megs in this case. So obviously that isn't an instantaneous response. The blue line here is the instantaneous response. So we using the flywheels, ultracapacitors, and the load bank, we can shape the overall response such that it does match this blue trend. So when called, the ultracapacitors and flywheels immediately release energy, and this begins to dissipate as they run out of juice. And this is controlled in such a way as to create the necessary surplus to make this a straight step change and a flat line. When the power falls below zero, the load bank now comes in and takes load off the power output, which basically negates this overshoot. So the net effect is to have a flat 2 megawatts. So these graphs here kind of further illustrate the same point. This is in the left graph here, we're following a set point which is in a black dotted line, and we have the turbine's response, or the generator response, which is the light gray line here. So you can see it kind of fluctuating and sorry, that's incorrect. It's the dark gray line here. We have this here following the load as best it can. We also have the black dark line is the site ancillaries. So this minus this is the net output onto the grid. And then finally, we have the light gray, which is the hybrid frequency response system. So the ultracaps, the flywheels, and the load bank are basically taking up the slack to allow this response here, this red line, to follow the dotted line insofar as possible. So you can see this is an actual trend and it follows it quite closely. On the right hand side, you can see we were able to do a lot more complex responses. So this is a site set point for load following and for frequency response, and you can see that it's quite a complex waveform, and basically we're following it. And the orange line here, if you can just make it out, is our turbine response, and the yellow is the ultracaps, and the purple, which isn't required for this particular one, is our load bank, and net effect is the blue, is following the blue shape. So finally, just to kind of talk about experience and lessons learned. One of the main benefits we got was out of this system was a lot of the validation work we were able to do with our models on our high-grade cold store system and our thermal storage system. So the graphic on the right there is a it's a bit old now, but it's an early CFD modeling we carried out on the high-grade cold store. And we were able to match up the experimental data with our models to ensure that we could capture the propagation of a cold front during charging and discharging to an accurate degree. We did something similar with our thermal storage system to capture to model the stratified tanks and to see how the thermocline within it would move. So in general terms, though, from a plant point of view, how did we get, what are our lessons learned in our experience? We startup optimization, we managed to reduce the startup time by a few minutes. So a lot of those idle speeds I showed you, and some of the synchronization time we managed to reduce with just clever changes to the control system, and also working with the OEM to make that happen. We validated our startup strategy, so the use of the cryopump as the main power governor, and then using the cryopump and inlet guide vanes, or on a larger scale plant, inlet valves as a means of precision control for a speed ramp. So together we were able to validate how to start this plant, particularly as it's a Rankine cycle in sliding pressure operation. So a little bit different to how a steam turbine would work in a steam plant. We also did a lot of loss optimization, particularly around things like seal gas philosophy to reduce seal gas requirements, and also to minimize the losses of cryogen during standby, during thermal readiness. Instrumentation, the key take home is over-instrument your plant or system. Some of this is obvious. Troubleshooting problems during commission and operation, you will 100% regret not putting a flow meter or a temperature sensor somewhere in the system, because maybe you were looking at it from the point of view of just what's necessary for the basic process system or the safety systems. So it's definitely worth over-instrumenting your plant, which will save you a lot of time during commissioning and operation. Also, analysis of the systems in subsequent years. So, even to this day, we're still analyzing Pillsworth data to further optimize what we do. And sometimes, you kind of regret that we didn't stick an extra temperature sensor somewhere to I don't know, analyze an aspect of heat loss somewhere. So definitely worth taking that into account as well, what analysis you might want to do after the plant, if not during it. Redundancy on safety critical instruments is an important aspect as well. It always pays to have a number of redundancies. This fits into the next point, which is to say, choose quality instrumentation. Relatively inexpensive to buy, but can be costly due to downtime if you have to replace a key sensor somewhere and you're no longer available to run. So definitely choose reliable quality instrumentation, even if the cost is a bit higher than the cheaper version. Construction and commissioning for us highlighted serious advantages to creating modular subsystems. So again, commissioning time and commissioning cost are huge aspects of the whole construction and getting to operation. And we found that if we could modularize our design, so take a number of heat exchangers or a system of heat exchangers and have it fabricated off-site and put together on a skid, and all the various control and electrical systems, cabling and control could be tested off-site, then this potentially massively saves costs for on-site commissioning. So this is one take-home point we had. In terms of co-location, both the Pillsworth plant and the Slough plant were co-located with heat sources. And as a result, we've gained a lot of expertise in sort of just taking into account intermittent heat sources when co-locating, because you don't necessarily always have the heat when you want it, particularly if you're dealing with another company who dictates when that heat is available. So this is something to take into account. And finally, the last point I would say is that we gained a lot of experience as a technology developer to inform and collaborate with OEMs and EPCs. So a lot of the times OEMs and EPCs want to do things a particular way because of their experience and how they've always done things. And given that this is, new technology and we're using similar kit and similar cycles, but we're operating it in a different way, it pays to be able to be informed and to be able to collaborate with EPCs during feed and with the OEMs to come up with an optimal design. So this was a lot. And I mean, for example, cutting off the time for our startup was an example of that, where we worked very hard with the OEM to figure out how we could shave off a few minutes here and there. So that, I think I'm pretty much on the money there with 30 minutes. So that's everything. Apologies if that was a bit fast. If you have any questions or need to address anything again, please send a question and I'll try and answer it in the Q&A section after the next presentation. Thank you very much for your attention.
Thank you very much, Johnny. Very, very interesting presentation. And definitely a lot of possibility for questions here. So we have a few questions in the chat. We will pick them up later, as you mentioned. So just to remind everybody, please feel free to drop further questions if you have them here. We will have a little bit more time for a Q&A after the next presentation. So I would like, therefore, to now invite Dr. Stuart Scott from the University of Cambridge. So Stuart, please, the floor is yours, and we are looking forward to hear the advancement there at your institution.
Okay, just a moment, let me.
Yeah.
So is my screen visible?
Yes, perfect.
Okay, well, thank you for this opportunity to speak. My name is Stuart Scott. I work in the engineering department at the University of Cambridge, although I'm really a chemical engineer hiding in the mechanical engineering department. And it's important to say that a lot of the work I'm presented has been done by my PhD student. You can see here, Mohammed, who deserves the credit for all this kind of work. So I'm going to focus on just one aspect of energy storage that I've been working on, but I wanted to just acknowledge the wider research effort that's taking place in our department on particular thermal storage. Alex White's been leading this effort for quite a few years, and you can see that this has gone from looking at cycles through to generated integrated storage. And really my contribution was that I had previously worked on various thermochemical cycles where we use chemical reactions to do things like hydrogen production, and we wanted to see if we could integrate these into the kind of schemes that Alex was working on. And in particular, you'll see that I'll be talking about this thing that we've called chemical looping energy storage, and the work has been done, as I say, by my PhD student here. Now, some background, and it's a deviation really from energy storage, just to show where I came from. My previous interests were in making use of reversible chemical reactions in cycles so that you could use them, for example, to do things like combustion more efficiently or to produce hydrogen. And one that is often cited is this chemical looping combustion cycle, where you use a cycle of oxidation reduction of a solid to transport oxygen from a fuel to produce CO2. For example, I use my pointer here. Oh, sorry, if I go back. You take something like copper oxide, a solid, and you take pellets of this copper oxide and you mix it with a fuel to produce carbon dioxide and water. So you do the combustion and the metal gets reduced to a metal. And there, what you've managed to do is carbon capture, because you have a stream of CO2 that's undiluted by nitrogen. And then you complete the cycle by performing an oxidation reaction to release heat. And so you have a solid oxide oxygen carrier looping between two states, an oxidation and a reduction reaction. And so hence the term chemical looping. And so we worked with lots of these kind of cycles to, as I say, produce hydrogen, do carbon capture, produce oxygen. And in the context of energy storage, well, really you've got the ability to make use of the delta H of these reactions. So chemical looping uses a solid carrier, which can undergo a reversible reaction to transport a reactant from one system to another, or to save it for a later time. And that's the key if you're doing something like energy storage. And the focus here, in terms of energy storage, is on the combustion reaction of something like a metal oxide that can be reversed. And so if you look at something like copper 1 oxide here, Cu2O, if you burn that with oxygen, you can make black copper 2 oxide, and you can release energy. But this combustion reaction is reversible. So if you get the conditions right, you can reverse it and you can make this black copper oxide here decompose to give you red copper oxide and release some oxygen. So if you're interested in this kind of thing, clearly the equilibrium constant for this reversible combustion reaction is going to be the key thermodynamic constraint. And it's what really decides which material can be used and in what context. And what I've done here is, rather than look at one material like pellets of copper oxide being combusted, I've done it for a generic metal oxide, which I've just called Me for metal. And so what we're going to do, or what I'm going to do in this talk, is really try and cover all possible materials by trying to characterize the reaction and the materials by some properties of the reaction, rather than just looking at one material. Now, if you look at the equilibrium constant for this reaction, you find that you can express it in terms of an equilibrium partial pressure. And you can see that this depends on the heat of reaction, this delta H, and the entropy of reaction under standard conditions. And so you can characterize the material entirely by these two parameters. Now you can plot this out on a graph, this phase diagram that you often find if you do metallurgy for oxidation and reduction of metal oxides. And basically, you have an equilibrium partial pressure that varies with temperature. If you are one side of this equilibrium line, so if you're at a pressure that's below the equilibrium pressure or above the equilibrium temperature, then you can cause the system to produce oxygen by decomposing the metal oxide. And if you are above the equilibrium oxygen pressure, you can reverse the reaction and release energy by combusting the metal or metal oxide. And so now what you've got is a trigger that we can use to move the reaction backwards or forwards, and we have a large heat of combustion that we can use for storage and energy release. Now, I said that we can characterize pretty much all materials by their equilibrium constant for this reaction, and this is a function of the heat of reaction and the delta S of reaction. Now, it turns out that if you look at most metal oxide systems, the delta S of reaction is fairly constant. So it ends up being about 200 kilojoules per mole. And so instead, joules per mole per Kelvin. And so instead, we really just need to worry about this delta H. So what I've done here is just plotted out different materials. Rather than label them as different materials, I've done it in terms of the delta H. So the parameter delta H is now the thing that we can use to characterize each material. And something like copper oxide, Cu2O, will be a line over here. It's not far off this 125. And other materials, other metal oxides will have different heats of reaction. So rather than looking for a specific material and do an analysis of a particular scheme for a particular material, instead what we wanted to do was look at all possible materials and just see what space was available to work in and whether or not we could integrate these kind of reactions in something like pumped thermal storage. So the question we asked ourselves was, given a fixed configuration of plant, what delta H would give us a good performance? And then separately, can we go and find a material that would meet that delta H? And our starting point for this analysis was really to look at some existing schemes that in particular my colleague Alex White was working on, pumped thermal storage, and see if we could really try and integrate these chemical reactions into the pumped thermal storage, so that instead of just relying on sensible heat to store energy, we could also use this delta H, this reaction heat, as an additional storage mechanism. And in pumped thermal storage, and I'm sure this is known to most people in the audience, you take a gas, you compress it to a high temperature, you store the heat of compression in a heat front, and you also store some cold energy in a cold front when you're charging, and to discharge, you simply reverse the cycle. So you have two beds and you have a hot and a cold front, and you manage the front, and you can get reasonable performance by doing this. Now, if you try and integrate a chemical reaction to this, it turns out to be quite difficult. For example, you could take the argon that's going around this cycle here and use the compressor to increase the temperature sufficient to cause decomposition. And if you did that, you'd have a hot front moving through your system, and you'd have a decomposition reaction that's absorbing energy. But coming out of your reactor, you'd have not just argon, but argon and oxygen. And then the question is, what do you do with that? Well, you'd have to either get rid of it or store the gas, or you'd have to have a bed here, the cold bed, that's able to absorb oxygen. And so this is not impossible, but it's really a very difficult thing to arrange, to find different systems that can do this. The other alternative would be that you'd have to have methods of storing this oxygen-rich gas from the charge cycle ready to be used for the discharge cycle. So you'd end up storing large quantities of gas between cycles. And again, that's probably not going to be feasible. Now, this is the basis for things like chemical heat pumps, but in the context of energy storage, it just turns out that if you sit down with a piece of paper and try and figure out how to do it, it's just really quite difficult to come up with an arrangement that can exploit these combustion reactions. So really that pushes us towards open cycles. And we could, of course, use an inert gas to trigger the decomposition. So we could, for example, compress some nitrogen or argon or any inert gas up to a high temperature, run it through a packed bed of metal oxide pellets and trigger a decomposition, which I've shown here. So here we have, at this end, we have material that's decomposed, and at this end, we have material that's yet to be decomposed. And we end up with a reaction front running through the system. Now, The problem with this is we then make nitrogen plus oxygen, which is fine, but we need a supply of nitrogen, which we could get, ironically, from the discharge cycle. So during the discharge cycle, we could reverse this whole process, reverse where the front goes and extract work and make nitrogen. The problem is that we end up storing huge quantities of gas between the charge and the discharge, which kind of defeats the purpose when you look at things like energy density. So that really then pushes you even further to using air as the working fluid. And if you use air as the working fluid, providing you have a sufficient compression ratio on your compressor, you can get to a high enough temperature to trigger the decomposition reaction. And you then end up with a stream leaving your system that contains air plus some extra oxygen. Now, this is much more tightly constrained now because this temperature that I'm putting into the bed here is a function of the compression, and it has to reach a certain critical value, otherwise I can't trigger the decomposition reaction. So the fact that it's tightly coupled becomes important when we start to look at how we optimize the system. If we look at what's actually happening in these beds, and this is where it does differ to pumped thermal storage, is if you look at this simple system and allow the pressure ratio to be large enough to cause this inlet temperature, this TC, to be large enough to cause thermal decomposition, two things happen. First of all, you get a fast heat front that propagates through the system ahead of the reaction front. So there's no chemical reaction, and this heat front simply sweeps out the initial temperature of the bed. So very much like the kind of heat front that you have in the standard pumped thermal storage system. Behind that, you form a much slower reaction front. And it's the slower reaction front where you have the reaction happening, you have the heat of reaction absorbing energy, and you have a temperature drop caused by this heat of reaction. Now, in reality, both fronts will be diffuse, and we have been looking at models of diffuse fronts and trying to work out how they'll behave. But for this analysis, what we decided to do was, just because we want to optimize many different configurations, we've taken the limiting behavior and assume that these fronts are sharp fronts so that we can effectively look at lots of different configurations and come up with an analytical expression for how each of these fronts will behave. And this limiting behavior, you could argue, is very generous in terms of evaluating the performance of the system. But if we're operating with sufficiently fast chemical kinetics, with sufficiently large beds, and with sufficiently favorable Peclet numbers for mass and heat, then this is not a bad approximation. And we see fronts like this forming in many of our experimental systems. Now, on discharge, on charging, we have air and we produce some air plus some extra oxygen. We don't want to store this. So storing the extra oxygen that we produce, really, again, it will defeat the purpose because we're having to store gas. So we throw this away, and on the discharge cycle, we reverse the process and we simply have, we use air and we have a system that removes oxygen from the air. And so there's a slight loss associated with that. Now, if we look in more detail at how these fronts behave, well, if we use perfectly sharp fronts, we can simplify the system and we look at this charging behavior, then we're constrained by the fact that on our phase diagram, our inlet temperature, this T that's over here, has to be in this region of the phase diagram, so that when the gas enters the bed, across this front, we get a temperature drop, and this point shows the temperature leaving the front. And so we're constrained to operate in this side of the phase diagram. So where this line is very important. So different materials change where this line appears, and therefore change the operating conditions that we can use within the system. So the problem is very tightly coupled. If we then go to the discharge cycle, we end up having to work at the opposite side of the graph. So on the discharge cycle, we put air in, and this discharge temperature now has to be sufficiently small that it can trigger oxidation, so that we end up on this side of the graph. And so the fact that we're using compressors and turbines to provide the temperatures in discharge and compression means that we've got a very tightly coupled problem. So in terms of optimizing it, you find that there are only certain regions you can operate in for a given material where this is even feasible, even when you do this very simple analysis. So in general, we decided that storing the gas was probably impractical, and that led us to open systems. We decided to use air, just because that's a very convenient working fluid. We need to use different pressure ratios on the charge and discharge because the discharge temperature has to be lower than the compression temperature in this particular system because of the shape of that equilibrium curve. And we use single bed systems because it was very difficult to arrange a multi-bed system when you're dealing with chemical reactions. And this, of course, means that we have lots of losses due to the fact that we're exhausting gas that might have a work potential. And so part of the reason why pumped thermal storage has 2 beds is to prevent these kind of losses. So again, you might expect this not to be a particularly efficient system. The operating regime is highly constrained by the chemical reaction, which here, of course, we're characterizing by the delta H of the material. And effectively, your pressure ratio ends up being linked to the heat of reaction that you have for your material. So you can only operate at certain points on that phase diagram. And so this ends up being something that becomes quite limiting when you look at how you could optimize the system. We also have 2 heat storage mechanisms. The first is we have a reaction front that's absorbing a large amount of heat. And also we have the same front that you would have inside a pumped thermal storage system where we're storing heat in the sensible heat. And so you might expect that capacities might be higher than pumped thermal storage. Now, what we did, because it turned out to be quite difficult to work out which systems would work and how to optimize it, is we allowed the material to be a parameter. We characterized it by the delta H, and we asked the question, if we could select any material, sweep all possible delta H's, sweep all possible temperatures for discharge and compression, where would be the optimum? Where could we operate? And we found that there were effectively 2 competing effects, 2 competing objective functions. The first is the capacity, and the second is the round trip efficiency. And we also had to constrain things like the compressor outlet temperature to something sensible. So we chose 900 Kelvin, not necessarily because it's correct, but because it leads to sensible numbers and means that you don't have compressors that are producing incredibly high temperatures. When we ran this optimization and got the Pareto front, which you can see here, and what I've not shown here is the one we get if we use ideal turbo machinery, we find that the efficiency is really quite low. So if you use very efficient turbo machinery, isentropic efficiencies and polytropic efficiencies of wood, you get a very, very good system. But it's very sensitive to turbo machinery losses. So as soon as you put in a sensible isentropic or polytropic efficiency, you end up with round trip efficiencies down at this very low level. So it doesn't look good, at least in this configuration. We get the expected trade-off between round trip efficiency and capacity. As we sweep along this graph, we're looking at the optimum for different materials, and this is why the delta H is changing. But all these delta H's are material, we'd be able to find materials that can operate with these particular delta H's of reaction. And if we just zoom in and have a look at the behavior at different points on this curve, at let's call it the high capacity end, if we look at the exergy balance, and if you don't like the word exergy, just think of it as where the work has gone. So here I have this on the left-hand side, I have so much electricity going in, and this graph just shows where it goes. Out is this bar here, and each of these bars or these arrows show where the electricity is dissipated in losses. And you find that the high capacity end, you're losing a huge amount of work potential effectively in your turbo machinery losses. And this is partly because we're constrained to work at quite a low temperature by the compressors. If you go to the other end of the curve, and let's call it the high efficiency end, and I use the word high somewhat advisedly because it's not particularly high, but relatively high efficiency end, you find that if you repeat this analysis, it's really the large exhaust losses that are penalizing you. And that, again, shouldn't be a surprise, given that we've not done anything about the fact that we have high temperature and low temperature gas leaving the system, which could have gone into a cold or hot start. So with the simple system, we can come up with schemes that work. We can come up with an operating map and understand where the material, what kind of material we should use, but the performance is terrible. We end up with very low efficiencies, and really it shouldn't be a surprise given the fact that we haven't attempted to recover any of the work potential in the exhaust. So what can we do that's better? Well, the first thing is to deal with the exhaust losses, adding a recuperator fixes most of that problem. So if we simply add a recuperator to recover energy from the exhaust, both in charge and discharge, we can improve the performance of this system dramatically. And you can see here, the red is the previous graph. So it's the same graph, it's just on a different scale. So this is the previous cycle, making use of an unrecuperated system with its very low efficiency. And as soon as we add the recuperator, suddenly our efficiency gets much bigger and our capacity becomes very large. And so we're now in a situation where it's starting to look like it might become a good idea. Another point to note is that we've maxed out the compressor temperature, the charge temperature at its maximum. And this really is probably obvious given that we're dealing with modified Brayton cycles, where if you increase the temperatures that you're working at, the compression ratios, then you minimize the effect of the turbo machinery losses. So you don't minimize the losses, but they become less important as a proportion of the work outputs. And so we find again that we become limited by this compressor charge temperature here. And so the temperature coming into this bed becomes our key limit. And because we're limiting ourselves by having a fixed type of turbo machinery that can only produce a certain temperature, this limits the types of materials we can use, because we can only use materials that can decompose between this 900 Kelvin. And so we become limited to low materials that have a relatively low delta H, and we're limited to materials that will decompose at a relatively low temperature. But at least on paper, and on this first sweep of analysis, we end up with something that looks like we can get a pretty good charge capacity and discharge capacity and a reasonable round trip efficiency. So where would this be compared to things like pumped thermal energy storage system? And here are some numbers that we produced by producing some comparable models. And what we find, and this really shouldn't be a surprise, is that by integrating a chemical reaction and making sure we have a recuperator so that we don't throw away the exhaust work potentials, the chemical reaction increases capacity. And really this is why it's there. We have a delta H to absorb a lot of the thermal energy. So it's no surprise our capacities are significantly higher. And we end up with a round trip efficiency that's a bit lower than if we did pumped thermal storage. And again, this shouldn't be a surprise, because by adding this chemical reaction front into the system, we now have an extra mechanism to generate entropy. So we have the entropy of reaction, and we typically are running this reaction away from equilibrium. So we have an extra source of thermodynamic loss. So we end up with a system that's intermediate between pumped thermal energy storage systems. So in terms of efficiency, it's a bit worse, but it's got a much better capacity. And somewhere between a hydrogen production and storage system where we have much lower capacities, but perhaps comparable or even potentially slightly better efficiency. So it should be no surprise really where we ended up in this particular scheme. Now the question is, can we find materials? Remember, as we sweep along these curves, each one of these crosses represents a different material, each with its own delta H. So can we find materials that do this? And what we have here is, I admit, a slightly messy slide, and it's messy because we plotted on these phase diagrams for lots of known materials. And these are the usual suspects if you work on chemical looping with metal oxides reduction and oxidation cycles. Typically in chemical looping, we work at the right-hand side of this graph at the high temperature end, where you have to heat things up quite a lot to get them to decompose and produce oxygen. Now, at the left-hand end, we find that we have materials that decompose too easily, and so we'd have to run the cycle at much too low a temperature. And in the middle is where this analysis puts us. So it puts us in this middle temperature range, and we're limited by the compressor technology. So the only reason we're not able to go to the higher temperatures where we might like to be is because of the compressors. And so we find that we can't use materials that I would be more used to working with, like the copper oxides, the cobalt oxides, the manganese oxides up here, because of this compressor inlet temperature, compressor outlet temperature issue. So if you look at this simple cycle, you end up finding that you could use things like lead oxide decomposing, or even manganese oxide. Now, lead obviously is not nice, and certainly if you work in chemical looping, you never consider working with these kinds of materials. Manganese oxide looks feasible, but people who've worked with this in the chemical looping context have always found that manganese oxide is quite difficult when you work at these moderate temperatures, because although thermodynamics suggests it can be used, chemical reaction kinetics tend to be very slow. So you find that you can do a decomposition reaction easily enough, but the activation energy to go this way is quite high. And so you find that often you can't reoxidize the system. So, you know, in theory, we can find simple materials that do this, but in practice, many of the easy materials that people know about won't work. Now, that's not to say we can't find other materials. These are just the simple metal oxides. There are lots of other combinations of mixed metal oxides that you can tune to give the thermodynamic properties you want. But these are the ones that be on the sort of first list that you might try. And the reason we have this problem is that the material space that we can work in, the delta H's that will work, are highly constrained. The equilibrium curve and energy balance across the reaction front tie the charge temperature to the charge pressure ratio. And we can't get the charge temperature high enough because we're limited by compression technology. So it's effectively the fact we can't get to a high enough temperature that limits us to these materials that are not usually used in chemical looping context. Now, how do you get around this? Well, there are two ways you could potentially get around this problem. You want the materials to decompose, and so you can trigger decomposition by increasing the temperature or by lowering the pressure. And so we reconfigured our flow sheets and added in some extra options so the optimizer could do this. And one thing you could do is you could have use vacuum to lower the pressure. So we added the option so the optimizer could select either the compressor or a vacuum system. And we also added a heater. Now the heater does two things. It doesn't just boost the temperature, it adds an extra degree of freedom. So it decouples the pressure producing system from the temperature at the inlet to the bed. And this turns out to be very helpful. So if you use an electrical heater, normally thermodynamics says it's a very bad idea, because in thermodynamics, the idea of turning electricity into heat usually causes people to worry about the losses in work potential. But partly this is fixed by having the recuperator. This heater isn't having to heat up the inlet gases from ambient. Now, when we throw it at the optimizer, we find that the optimal charging system turns out to be remarkably simple. And perhaps it's obvious, but certainly it didn't occur to me that it would be this straightforward just thinking about it. The optimal charging system is simply to have, and it's not shown, but simply a very low pressure blower blowing some gas through the system and using an electrical heater as the sole source of work input to the system. You then end up with the potential to create a very high charge temperature. You end up with a reasonably high exhaust temperature, but you recover a fair amount of that through the recuperator. So the exergy losses due to the exhaust are not too bad. And the fact that the heater is operating between relatively high temperatures, a very high temperature difference here, means the electrical losses are not as bad, or the thermodynamic losses due to electrical heating are not as bad as you might expect. Now, it is true that a compressor heat pump system like the Brayton cycles that we've used before and in pump thermal would be more efficient than the heat pump if they could hit the same charge temperature. But here, you simply can't get a compressor that would ever give you the kind of temperatures that we're talking about. And so really what we're saying is that by having a nominally inefficient electrical heater in the thermodynamic sense, it's more important that this allows us to go to higher temperatures than the losses that using the electrical heater causes. And so we'd never be able to get to these high temperatures using the heat pump system. And if we can go to a high temperature, then we can use materials that will decompose at high temperature. And because of the shape of the equilibrium curve, these materials have a high delta H. So they have a huge capacity, much higher capacity for storage than the materials that decompose at low temperatures. And so if you do that, you can get into the realms where you end up with very, very high capacities, really high capacities and really quite good efficiencies. And it's because, as I said, we've been able to push it into a regime where we can start using materials that are more familiar to people who work on chemical looping. materials that are towards the right-hand side of this curve. So things like copper oxide, manganese oxide, all these have been suggested as things that can be used for chemical looping. Barium oxide, by the way, was used to produce oxygen in the Brin process in the 1900s. So these processes do exist, and they've always been at this kind of end of the temperature scale. So moving to higher temperatures puts it into a space where we can work with pellets of material that we're much more familiar with. And these high delta H materials are really quite commonly found in the field of chemical looping. And there's been lots of development work gone into producing pellets of these things. And in fact, here you can show a picture that I've taken from some old work from one of our PhD students from 2009, where we were using pellets of copper oxide, which is one of the candidate materials. And in this context, we're using it to provide oxygen to a fuel, but we heated it up to nearly 1200 Kelvin. It decomposes to produce oxygen, and you can see that the color changes. So as it decomposes, it goes from black copper oxide to red copper oxide. These happen to be used in a fluidized bed, which is why they're small rather than perhaps the larger ones you'd use in a packed bed. But one of the issues that we're going to have with this material is really that these materials don't have to undergo many cycles of oxidation and reduction, and they have to go through quite a severe process. And so there's been a lot of work going on in really stabilizing these materials. So to conclude, because I realize I'm just over time, we did a limiting analysis and we mapped out favorable configurations and what I've called the material space. We get storage capacities in excess of pump thermal and comparable efficiencies to hydrogen, but I mean, and of course this always comes with a qualification. This is a very favorable study because it doesn't consider really the practicalities of doing this. And so obviously, you know, things like we should be looking at better models to estimate likely losses, better models of real turbo machinery, looking at what it would take to build a practical system, development of the metal oxides, and we've not really focused on the costs. And one of the things that will become important is the costs of the oxide material that's used. And this can be from almost nothing to very expensive, depending on how you engineer the oxides. And finally, I really have to acknowledge that this has been done by my PhD student, Mohammed, who's really working this topic. His email address is here. He is really the brains behind all this, and these are all his ideas and his work. And really thank Alex White and his workers for both their patience and help in this effort that we've been engaged in. So thank you.
Fantastic. Thank you very much, Stuart. That's very, very interesting presentation. So we have certainly time for questions. We have, well, approximately 45 or so minutes for question and discussion. So I would like to well, remind everybody that you can drop your questions in the chat box, or you can also raise your hand again with the Zoom facilities and unmute yourself to ask directly the question. So I took some questions from both the presentation. I see Yulong might want to ask some questions. Yulong, please go ahead.
I'll ask Johnny a couple of questions first, and then ask Stuart one. Would that be okay with you? Sorry, I'll ask quick one. So
no, go ahead. We have plenty of time. Okay,
Johnny. The load bank and the silk caps for the frequency regulation. I'm just interested in what's the fast response you can get, because from the diagrams and you present, I wasn't really quite sure. Is that seconds, few seconds level, or millisecond level?
So the number I have is sub-second. I'm not quite sure. Can't go to any more accurate numbers than that, but that's for the static response. So the getting to the 2 megawatt set point, that was approximately sub-second response. It's obviously a bit harder to kind of answer the dynamic response because it's constantly jumping around, but yeah, sub-second.
Right. Okay. Great. That's the first. Second question is about adding those sort of function, because you know, the thermomechanical storage systems have been criticized for sort of not able to respond for the, you know, the primary frequency response. I think clearly you have shown that that can be done. And so how much cost does that part add to the, I mean, as a percentage, rough percentage, Would you be able to sort of tell us?
That's a very good question. I don't have an answer for you on that, for the reason that it's not something which we've had to look into implementing for our commercial scale plants. So it was something that we wanted to prove at Pillsworth, and it's potentially the sort of sub-second response or the frequency control indeed is something that we could investigate in future plants. But with the revenue stacks that we see as being the most likely for us to participate in for both the plant at Carrington and in the west coast of America, sub-second response isn't sort of necessary, so we've kind of avoided it at the moment. So it's kind of in the pipeline, but not just yet.
I see. I mean, the load bank is about heater, and of course the control system is quite expensive. Understood. So
exactly, yeah. I mean, there might be some for the load bank response. You might be able to sort of integrate the heater into the molten salts tanks, for example, because you've got heaters required there for maintaining temperature set points. So there could be a little bit of an overlap there to cost save. But in terms of getting the hybrid system, so ultra caps or flywheels, that's something which you have to consider as well.
Yeah, understood. Thank you. Last question is about the pressurized ethylene glycol water system. So could you shed a bit of light on why you want to pressurize the ethylene glycol water system? Is that a sort of a main effort to bring down the boiling, bring up the boiling point?
Exactly. Yeah, that's the only reason. The ethylene glycol, apart from acting as an antifreeze, actually slightly favorably changes the boiling point, so that the pressure doesn't have to be as high as if it was just water, but you still have to do pressurization to sort of over 15 bar if you want to avoid the boiling problem.
Okay, thank you very much. So I'll sort of start asking. So I have a very quick question for Stuart, if okay with you. So I mean the control of the from materials perspective. I mean metal oxide. Clearly, we know there is a problem with the degradation of the material, and also because the reaction rate is likely to be controlled by either mass transfer or heat transfer or possible other reasons. And how do you see how we might sort of match that to the turbo machinery, because the turbo machinery would be a fairly fast response, and but that sort of reaction from heat mass transfer are quite difficult to control. How you think that might be matched sort of for potentially future operation aspects?
Yes, it's well. So I think the issue is really that if you're working at sufficiently high temperatures, and there's actually been a fair amount of work done with chemical looping in packed beds, in fact, for carbon capture. So again, this is not a field that's entirely unknown. It's not my work, but there is work in the literature. And the trick really is that when you're working at these very high temperatures, if you can get to high temperature, the reaction rates are so fast that they become limited by mass transfer. And that means that your control problem, that is sufficiently fast to give you a sharp front. So as long as you're sufficiently fast to maintain the sharp front, then it's fine. And certainly for the copper oxides and things like that we've worked with at those kind of temperatures, when they're fresh, these materials will do that. I think the issue is more what happens is whether the kinetics degrade as you cycle them. So what tends to happen is if you're working with copper oxides at very high temperatures, even if you're not near the melting point, you're close enough to the melting point that you get sintering, and you get the chemical stresses. And so I think the work to be done in these areas, and it's a bit I have more knowledge on, I'm not so good on necessarily the turbo machinery side, that's more Alex's thing, is really how you get the material to withstand the stresses of doing this. And copper oxide, for example, stabilized on alumina, will happily operate quite close to melting point for 100 cycles. There are other materials where when you do a phase transition, you don't actually result in a phase transition. So you can take oxygen into and out of the material, but the bulk oxide stays the same crystal structure. These are called perovskites. Now they're quite low capacity, but it means that you can bring oxygen in and out of the structure infinitely, and there's no real change to the material. So it doesn't degrade. So I think there's space to work, but for me, it's probably the most difficult and interesting challenge is finding something not so much that doesn't have kinetics that allow it to work at the start, but allow it to work after 100 cycles of charge and discharge.
Okay, so just a very quick last question for Stuart. Is the I mean, thermochemical storage has been seen as sort of a media to long-term storage technology, and if we do think that way, then the turbo machinery investment in turbo machinery is high, and also you operate a couple of times a year, or a few times a year. So from the revenue or economic perspective, how would you sort of think we might sort of get around of that challenge?
Oh, well, that's one of those impossible questions. I think, discussions with Alex, Alex very rightly is interested in cost, and I presented round trip efficiency, but really it's cost of storage and cost of discharge that are the real metrics. And I think the answer is I don't know. What we've been hoping to do is, and I'm going to hopefully have some students looking at this, is basically trying to see if you can do it with off-the-shelf components. I think the key with Johnny's presentation previously, he said something very interesting. He said we could do everything with off-the-shelf components, and I thought that was a very insightful statement. And I think if you were going to use this kind of technology, instead of engineering the turbo machinery, I think you would have to look at it from the other point of view. You'd have to work within the limits of what you could buy off the shelf. So the answer is I don't know, but if you were going to implement this, I think you'd have to do that.
Yeah, great. Thank you very much. I think probably my question was on if you invest in a sort of a turbo machinery, which is quite expensive stuff for that system, and you only use a few times a year, which means the percentage of time you use that is low. So just that was my question. So not the turbo machinery themselves. Sorry, I didn't make it clear.
I think your point as well also applies equally well to not the turbo machinery but the solid oxide. So Alex White was working on pumped thermal storage. They were using gravel that cost nothing. We are potentially talking about a metal oxide we paid for, which again, and that metal oxide only undergoing one cycle a year would be. So I think adding the chemical reaction potentially adds in a worse problem than the turbo machinery if that metal oxide formulation isn't cheap enough to be neglected. So I don't know is the answer, but I can foresee problems.
Thank you very much. It's a very interesting presentation for you both. Thank you. I'll shut up. Sorry.
That's okay. Thank you. Thank you very much, Yulong. Perhaps I'll pick some questions in the chat and start actually from one for Stuart. So one question came in asking if after the charging the store with the electrical resistors at high temperatures, could you actually discharge the system with a combined cycle gas turbine?
Definitely. And in fact, if you look on the literature, I think it would be unfair to say that we've invented this process. It's not like this process came in a vacuum. And there's certainly people have suggested that you would use these cycles integrated in with a gas turbine system. And in particular, although what we try to do, we try to avoid any external inputs of energy. So we've only used electrical energy in, electrical energy out. But previous works in this have assumed that you could boost the temperatures using the methane supply. So you effectively start combining the chemical looping plants that people have been working on for carbon capture directly with these systems and integrating them. In this work, we avoided that because we wanted to see if we could do it as a standalone system. But it does lend itself more to being integrated because in particular, you can reduce the metal oxide to different states when you have a fuel present as well. So you open up more possibilities in terms of how you run.
Okay. Fantastic. So perhaps I'll ask a question here also to Stuart. I'm interested again around the components of this system, in particular let's say the actual thermochemical stores. Are these or do you envision these to be essentially kind of off-the-shelf packet bed system, or do they require any particular, let's say, design configuration that makes these packet beds suitable for the actual process you are investigating?
No, I mean, it's a can of metal oxide pellets, I think is it's literally just a can. And we build them in the lab at lab scale and then nothing more in the tube. I think the challenge is that if we go above the 600 degrees Celsius that we're aiming for, we move out of pressure vessels that are made of standard steel. And so I think there's a danger that you end up in with expensive, exotic pressure vessels, I think is the danger. If I'm honest, I don't think there's anything special about it other than you might find that if you're at 1,000 degrees Celsius, you're talking about furnace type technology. You're not talking about pressure vessel type technology that's available. So it is off the shelf, but it's much more expensive. It's more like power generation technology. So that's, I think, a worry. I think there's that you end up that. Now, when you do it, you can reduce the pressure ratio massively. The chemical reaction, if you recuperate and use electrolyzers, the pressure ratios become quite small. So you might be able to argue that you're operating close to ambient, and so you don't need pressure vessels. Certainly on the charge, but the problem is, of course, during discharge, you would need the pressure vessel. So again, I think a risk is that when you start running to the high temperatures, that you don't have enough benefit to justify the exotic materials that might be needed.
Okay, fantastic, thank you. Yeah, so I'll probably pick a few questions for Johnny as well, and perhaps a few more questions will come in also for Stuart. So I think there were, in general, a few questions around the economics, the startup time, and configuration of the plant. So one of the first one was asking about how much space does this plant need, so the LES plant, and in general, if you can comment in what kind of energy system would be the plant work well.
Sure, no problem. Thanks for the question. So it really depends on sort of the how much storage you require, how much storage space you require, the size of the charging system and the discharging system. But to give you a flavor, for our sort of standard offering of a 300 megawatt hour storage system with a 50 megawatt power recovery unit and a 25-30 megawatt liquefier, we're talking about 12 to 15,000 meters squared space. In terms of what energy system, what I guess you mean sort of what revenues?
I believe so. Obviously,
sure. So
maybe I'll add a couple of questions or a couple of comments I had also from my side, which was during your presentation you mentioned some of the let's say power rating and storage capacity that might be more suitable for, let's say, the UK context or the American context. And so probably if you can comment about what drives those decisions from, let's say, revenues perspective or energy system context.
Sure. So in the case of the UK, it's largely to do with sort of the expected, by National Grid's expected amount of storage capacity you can provide for, say, the capacity market, and also sort of anticipated derating in the future, and around 300 megawatt hours or 6 hours of charge or discharge time, storage time, is kind of the sweet spot we feel for us. And in America, it really depends on where you're looking at the plant, but a lot of the facilities require quite large periods of discharge time. So it's kind of really what market you're trying to feed into. So if we go back to the UK for a second, like most energy storage systems and renewable systems, we're looking at stacked revenues. So it's not a single source of money you can get. And we're looking at capacity market, but in particular, we're looking at stability services, which are kind of the hot topic at the moment. So we've got inertia, which can be provided by our synchronous rotating equipment. We've got reactive power, which can be provided by our generator. There's various frequency response services you can provide. So the enhanced frequency response, which I showed for the Pillswick demonstrator, is not really applicable because we haven't got that, so we can't respond so fast. But there are kind of other forms of frequency response which we can avail of. There's also short circuit infeed, which is another. I think it's on National Grid's next Pathfinder, which is another anticipated revenue stack. And then you've got merchant trading, arbitrage, and a lot of other systems. So it's really kind of looking at sort of how you need to shape your storage system to meet the various requirements. So in the case of the UK, the capacity market is kind of the driving case for the storage system capacity.
Fantastic. No, thank you very much. So just flicking through the other questions. I think probably there was a question around the startup time. You probably have covered this one. So the question was, what is the targeted estimated potential for shorten the startup time? So to improve response time, is there any room for further improving the let's say startup time? Maybe I can add this.
Yeah, so that's a good question. So in our sort of, we took the lessons from Pillsworth, say for this spin gen mode, and we for our Carrington plant we've incorporated a clutch to decouple the generator from the turbine. This allows us to do a number of things. It allows us to use the generator to provide a lot of stability services, but it also allows us to keep that synchronized while the turbine can be stationary. And therefore, we're just using the pump and potentially an inlet valve to drive the steam derivative turbine up to nominal speed. So again, we've chopped out all of those synchronization, idle speed, waiting times. So we're looking at approximately sort of sub 5 minutes for the first plants, working with the OEMs, the turbine machinery OEMs, to try and get this down. There are some physical limitations on how fast you can start these pieces of kit, but some of them are kind of what sort of energy cost you're willing to accept. So a lot of, you know, as you probably understand, if we're spinning this turbine up very fast, there's a lot of physical stresses and thermal stresses which are undertaken. So one important thing to do is to make sure that your turbine is thermally prepped, either by some sort of electric blanketing or by other means of keeping it hot. So we keep the system ready for a hot start, and that allows us to ramp it up to higher speed as fast as possible. So we're looking at sort of sub 5 minutes, anywhere between 2 and 5 minutes. And if we require faster response, then as I was kind of saying to Yulan, we can explore the potential of building a scaled up version of the frequency response system if we want to compete. But at the moment, sorry, compete with batteries, I should say. But at the moment, the revenue stacks we're seeing can't make the economic case for us needing to have such a fast response.
Okay, thank you. I guess that your last comment answered one of the other questions, which was any plans to use the hybrid configuration flywheel supercapacitors also in the, let's say, full scale plant, 50 megawatt to 300 megawatt hour plant.
Exactly. So eventually I think it'll be important, but for let's say the first couple of plants, it's not envisaged just yet.
Okay, fantastic. Perhaps this one was one of the attendees asking about let's say, what is the optimal theoretically expected round trip efficiency and how close you are to that limit with the let's say full scale plant.
Sure. This is always a funny question to answer, because what is the theoretical efficiency of liquid energy storage? It really depends on how you tackle this. So if you get out your thermodynamics book and you start writing it down, and you kind of ignore, so if you get into a dreamland where you kind of ignore storage systems and you simply have your charging and your discharging system running against each other simultaneously, which would obviously be pointless, and everything's reversible, then your efficiency is 100%. But then reality kicks in and you need a storage system, and there's inherent irreversibilities of, you know, piping losses, finite temperature differences in heat exchangers, valve losses, etc. So it's the theoretical efficiency, if you take a certain slant at it, is 100%, but there's no practical upper limit, say like a Carnot cycle, at least none that I've come across yet in the literature. We see sort of 60%, in excess of 60%, as sort of the limiting case, say, for standalone liquid energy storage. For our first plant, we're sort of in sort of up to 50 to 55% efficiency. So the sort of there's a with all things there's a trade-off. We have to have as efficient as possible compressors, but have and expanders, but also have a certain amount of margin so they can operate at part load somewhat efficiently. So let's take the power recovery example. If we ask our turbo machinery vendors to design the most efficient impeller blades you can possibly get for a 50 megawatt net output system, then they can make that design point incredibly efficient. But as soon as you move off the design point, things start to get a bit hairy because your impellers are so heavily optimized. A similar phenomenon will occur on the compression train, where as soon as we move off, if we try and have a wide spread, so let's say a part load liquefier is desired, and we want to operate anywhere between 70% and 100%. You ideally want to make your compressor have a wide operating map, but also to have a relatively flat efficiency curve, so that you're not being penalized for moving off design point. So there's always a trade-off between maximizing compression and turbomachinery efficiency and the flexibility of the plant. So the further you go to the higher efficiency end, the more your plant is constrained to operate at a single point.
Fair point. Perhaps I'll take one more for your side, Johnny, and then I will ask a question to Stuart.
Sure.
If there are more questions, please, everybody, drop them in the chat or raise your hand. We are happy to hear from you. I think one question came from Brian, who is speaking later. Sounds interesting one. How does the economy of using liquid air as electricity storage compare to the market for liquid nitrogen as a commodity?
Yes, I was looking at this question. I was trying to figure out how to answer this one. So we're not so in terms of how Highview looks at energy storage, we're not looking at building an air separation plant, say at the tail end of our liquefier. There's a number of reasons for this. And the first would be that Linde and BOC and Air Liquide and all will do it much better than we will. But also because it also adds on a massive amount of time to your startup. So if you have to start cooling down distillation columns and getting them all set up for a certain amount of purity for your nitrogen and your oxygen, and if you have argon, then you've possibly changed. Air separation units run for years, 2-5 years without stopping. So you really want to start it. They're really designed to start up once or twice over sort of a 5-year period. So we don't consider it on our side. So we haven't looked at the economics there. If you look at it from the other side, from the cartel that is Linde and BOC and everyone else in the industrial gases world, they sort of have dabbled with liquid air energy storage, but have sort of never really fully committed to it. So possibly they're just happy making money off the commodity market, and and maybe someday they'll venture into energy storage, but maybe they don't see it as either too risky or not economical enough to make sense at the moment. I hope that kind of answers your question.
Yeah, well, I think the last comment, it's also quite interesting from an industrial perspective on how things are looked in terms of energy storage from Linde and these big players. But thank you very much. So perhaps I'm just a question from my side for Stuart around the modeling work and the screening for candidate materials. If that was let's say screening purely based on the let's say thermodynamic constraints and the equilibrium of the reactions, or did you include any let's say estimation of costs of those materials in the screening and potentially in their ranking?
Yes and no. Is yes in that it was a purely thermodynamic kind of, the material is characterized by the delta H. It's not entirely true. There's a little bit of wiggle room on the delta S, but these are sort of known factors. We included crazy things in there. If you just mine thermodynamic data, you'll find things like palladium, which clearly you'd never use. So in the sense that there's a first cut of economics, then you can go through and just do it based on, and we've certainly done this, not necessarily in the paper I mentioned, but it's what we're working on at the moment. You go through and you just list metal oxides based on their bulk cost on the open market, and it largely scales with that. You can, so things like iron oxide, copper oxide, even manganese oxide are the ones that you probably go for. So there are two elements to the cost though. One is, can you just buy it on the open market and use it, with very little modification, so an ore or just powders that you can agglomerate very easily, or do you have to do something if you're, for example, making a particular structure like a perovskite structure, where you then have to have a very expensive manufacturing process. So it becomes like making a catalyst. And so if you're making, you could find yourself making an expensive catalyst. And so that's kind of beyond the scope of what we're doing, but it's certainly in our minds that you've got these two approaches. Do you go for, simple, cheap, easy things to make, or do you go for much more expensive things? I think the fact that with energy storage, you are in a regime where you're discharging and charging less frequently than you might hope. You know, the whole point is you store energy for a long time. Whereas with chemical looping combustion, where you're doing carbon capture, you're cycling continuously. So the capital cost of the material, you know, it's being used efficiently, it's being used all the time. But if you're in a situation where you're storing large amounts of metal oxide for a long period of time, then that capital cost, I suspect, will push you towards the making it as simple and as cheap as you can, and using the, you know, the bare minimum in terms of processing of the metal oxides. So copper oxide ore, maybe, or, you know, powders that are agglomerated with cement, that kind of thing.
Okay, no, that's absolutely clear. I think I have a question from Angela. Angela, are you there? Do you have any questions?
Yes. Hi, Stuart. Thank you for the presentation. I just wanted to ask, do you think is any, do you believe that any metal oxides created, such as iron oxide or aluminum oxide, is on any danger of being a fine explosive powder?
In fact, aluminium oxide is an excellent store of energy, as evidenced by the fact it's used in rocket boosters. So you can view this process as a reversible rocket booster. The answer is yes and no with all these things. We're dealing with metal oxides that don't quite be, things like aluminium oxide, you can't, they're too difficult to remove the oxygen from by using thermal processing. So they wouldn't fall into the kind of things we use. So you simply wouldn't be able to use something like that. Other metals like copper oxide, if you have finely divided copper, they don't tend to explode, but you'll often get exothermic runaway. So if you have a large bed of copper oxide and you leave it alone, a large pile of it, you'll get you can end up with a pile of molten metal oxide if you're not careful. So I don't think explosion is an issue, but I certainly think there is a danger of exothermic runaway. And in fact, exothermic runaway is exactly what you have when you run the air through to regenerate the heat. It's just a question of making sure that it doesn't do it uncontrollably. So I think the answer is that we're not working with metal oxides that are likely to explode, but we're certainly working with ones where you could easily have a massive exothermic excursion. And in fact, we have to be quite careful in the lab. We never store the reduced forms of the oxides. So we tend to only ever store the oxidized form. We never, for example, make a huge pile of copper and finely divided copper and just leave it on the bench, because it will sit there and occasionally it will decide to ignite.
Thank you very much.
Thank you, Angela, as well. I think we have a kind of 7 minutes or so more. I think I have a couple of more questions that were in the chat early on. Let me just go through them. So one question again from for Johnny, it's about kind of the trade-off between the hybrid and the standalone configuration. So how much of the needed power change is globally delivered by the added hybrid, and how much by the, let's say, baseline LICE process? So I believe the question is about how much of the power output is actually delivered by the two parts. If it's truly an integrated plant, or ultimately is like a separate plant for frequency control.
Sure. No, so it's an integrated system. So it depends what mode you're in. So if we're in the dynamic mode, that is to say we're following the grid frequency. In that scenario there, it depends on what the active power error generated by the rate of change of the frequency is. So it will vary dynamically effectively. However, for the static mode, that is to say the mode where you're trying to ramp, you're ramping up your turbine and you're basically trying to fill in the extra area under the curve to get an instantaneous response. It's about 2/3 from the LICE plant and 1/3 from the FFR system.
Okay, thank you very much. I think we covered also some of the other questions. There was one question about if you are considering to integrate an air liquefier in the future plant. Yes. So the only reason we didn't at Pillsbury was really just a constraint on money. We had about 8 million from Bays, and we sort of had to figure out how to apportion that, and we focused on the discharge side because that's where most of the revenues are in energy storage at the moment, although that is kind of changing now. But yes, it's not, you cannot make liquid energy storage work if you are importing the product from say a BOC or Linde or whoever it is. So absolutely, yeah, we will be building a 25-30 megawatt liquefier. So roughly speaking, sort of 18 to 24 hour charge time to supply the product for a 6-hour discharge. Okay, fantastic. Yeah, perhaps I ask a question here from my side and from what we have, so to say, experienced in the work at the University of Birmingham. So working on the spin gen mode, partially turn the turbine in a sort of a compressor, and you have a, let's say, heat up of the basically the upstream pipeline, which might trigger some sensors, things like that. So how this is managed in if, let's say, the spin gen mode is actually implemented in the full scale plant?
Sure. So this is a problem which you have in all expanders, which they call ventilation. So if you motor it, if you have a turbine at low no load or very low load, and the volumetric flow rate is so low in your final stages that it effectively doesn't move, and then as you said, Adriano, it starts to compress. So you start to get a heating stage in your last stage in your system, and it's not something you can have for a prolonged period. Now at Pillsworth, this actually wasn't too much of a problem. It heated up to, I can't remember what temperature it was, but it wasn't risking the process. But this will be a problem if we use this mode for our steam turbine derivative. So particularly in the LP casing of the steam turbine. So as a result of this, we don't actually use spin gen as such. This was where the idea to use the clutch came in. So the clutch decouples the turbine from the generator, so we can basically motor the generator and provide all of the stability services required. And then when we require to run the turbine, we simply just use the cryo pump to ramp it up. It engages with the clutch, and now you want to get probably past sort of 20-25% load, and then you don't have a problem with ventilation anymore.
Okay, fantastic. Yeah, nearly there. I think I'll see if there are any hands up. I don't see anyone hands up or further question in the chat. Perhaps I'll take one last from my side, John, if you don't mind. It's around the let's say technical solutions you have implemented for the high temperature thermal store. So you mentioned it's a molten salt based system. Is this a single tank thermocline system? Is a two tank solution? Does it have any sort of filler, like a mixture of a packet bed and molten salts? What sort of a solution you adopted there?
Sure. So we've gone for a 2-tank solution, and this is largely driven by we're using a Spanish EPC called TSK, who have extensive experience with CSP plants in sort of Spain and North Africa, and so they have quite a good solution and experience with using molten salt. So it's a 2-tank solution, a hot tank and a cold tank, and we're using the molten salts as the heat transfer storage system, but we're using a thermal oil as the heat transfer fluid. So we're using Deutherme or similar thermal oil such as this. And the reason for that is because we want to try and localize where the molten salts are in the plant as much as possible. And molten salts, one of the downsides of molten salts is that they can freeze if you get them below. It depends on the temperature, it depends on the salt you're using, but let's say below 120 degrees Celsius, the salts can freeze. So you have to have triple redundant heat tracing. You have to have various means of ensuring that this temperature won't drop. So from a design point of view, it makes sense not to have the molten salts spread out around the plant. It just means having it locally kept in the salts tanks and in that kind of section. So you can use the thermal oil to as the heat transfer fluid, which interacts with the heat recovery system, the heat supply system, and there's a molten salt oil heat exchanger, and you impart the heat using that. So that's the solution we've opted for.
Okay, no, thank you very much. Okay, so I think we are almost at the end of this Q&A session. Any last burning question from the attendees and from the audience?
Can I ask Stuart one last question?
Yes, please.
Yes. Stuart, I just was wondering, what is your idea about using hydrogen as a reducing agent, and maybe the potential application of the metal oxides as a storage that maybe could be used as decarbonizing a sector like shipping?
So a lot of this has been looked at. So you can obviously reduce the metal oxide with hydrogen. From an energy storage point of view, it probably doesn't make sense. You can store the hydrogen just as easily as you can store the reduced metal oxide. So perhaps, so I think from an energy storage point of view, where it doesn't, I think what you're asking is really, can the metal oxide be used as an energy carrier? So can you, ship it around effectively? And
Yes.
It's just a bit heavy is the problem. So, the problem is people have looked at it, and if you go back to, you can find papers from the 1970s where people were considering, taking, it's called the steam ion reaction, the sponge ion reaction, where you take a bed of iron, foamed iron, and you pass steam over it, and you make hydrogen. So the iron is the store of energy, but of course a big block of iron is rather heavy. So what you're suggesting forms the basis really of either hydrogen production processes or attempts to use metals as energy carriers. And there is quite a bit of work on that. But what you tend to find is that for the ones that are easy to work with, it's really quite heavy. So it's not so bad if you're doing a fixed process in a packed bed, but if you start having to physically move the metal oxide around, it's not a great energy carrier.
Thank you very much.
Thank you very much as well. Okay, so we are spot on time. So thank you to Stuart, thank you to Johnny, and thank you everybody for attending the first part of the of this webinar for today. So we will restart at 11:30 UK time, and so we have a 15-minute coffee break. And so enjoy your coffee break at your place, and see you later.
Thanks everyone. Thanks Adriana. Thanks.
Thank you. Okay, so welcome back. I hope you had a good break, coffee break, tea break, or whatever your preference is. So welcome to the second part of the webinar for today. So we have a couple of more talks from industry, from academia, and further time for questions and answers. Actually some wiggle room at the end for further questions. So we say that this second part of the webinar focuses more on on some key components that are relevant for the Carnot battery concept, Carnot battery technology. So in this sense, I very much welcome Colin Grady from Heatrick, who will deliver the first talk. Colin, if you're there, the floor is yours.
Okay, thanks, Adriano. Just give me 1 second. Hopefully the slides are showing now.
Yes.
Okay, so thank you everyone, and thank you to the committee for the chance to present. I guess we've heard from a lot of the system providers, and part of that is we help them make the systems possible. So today I'll give you a quick overview of Meggitt and Heatrick. The main focus is on the PCHE and how they're made, with a very quick look at key markets and where we fit in the Carnot battery. I am going to go quite a gallop. Normally I'd do this in about half an hour, 40 minutes with questions. So we're going to condense it down. So Meggitt is a UK company. It's a FTSE 250, specializing in aerospace, defense, energy type applications. And we're one of the sub-companies and sub-technologies within that group. So it gives us quite a good platform on financial stability to draw on. So Heatrick are based in the UK with global sales offices. I won't dwell on them too much. So the main factory is down in Poole in Dorset. And you can see there's a virtual tour. The slides will be shared. You can have a look and prowl around the site, see what we do. In the UK, all the manufacturing, our design and manufacture is fully integrated. So it's all done in-house pretty much. So it takes us from the thermal and mechanical design through the etching, the bonding, the welding, and the testing phases. For many, PCHEs are what we describe as a 40-year-old new idea. They're not particularly well taught in some of the sort of base level heat transfer materials, but we've been around for 40 years, started in hydrocarbon processing, and we've advanced through looking at nuclear and energy storage and power generation. So we're quite a breadth of portfolio. So yeah, we cover offshore oil and gas type applications, onshore sort of LNG and LPG processing, marine for the transport of LNG and for powering the ships where they're using LNG instead of diesel fuel nowadays, and the power gen that's the focus today. So what is a PCHE? It's a compact type heat exchanger. It gives you the thermal performance that you might associate with a plate or a brazed aluminium type heat exchanger. The mechanical capabilities that you would normally only get out of shell and tube. And when you combine those, you actually get a superior safety and integrity compared to most other types of heat exchangers. And it's that combination of mechanical capability, thermal capability, and safety that really the energy industry, from hydrocarbons through to power gen, have taken advantage of over the last 35 years. So picture speaks 1,000 words. Shell and tube, traditional old style heat exchanger at the back, PCHE at the front. In terms of thermal and hydraulic performance, identical, but yeah, you're looking at 15 tons versus over 100 tons. That's footprint, that's structure, that's logistics and handling. Everything just becomes so much easier. And we're able to produce these, give you the safety that you need, the savings in terms of space, weight, and handling, the process optimizations, and we're doing it over a wide range of temperatures and pressures. So a typical compact exchanger is limited on the temperature and pressure range they can go to, be it because of gaskets or the materials of construction, where we are relying on material strength. The red curve there is just a function of the material stress curves that you would see in the ASME code. So to make them, we basically break it down to 6 fairly straightforward steps. So design, that's the thermal and hydraulic and mechanical constraints for each custom process. So it's bespoke design for your application to help optimize the process. Out of that, we then etch the plates, we diffusion bond them together, weld on some attachments, test it, and get it ready to go out the door. So looking at the steps themselves. So it's, as I said, it's a bespoke design unique to each process. That's to allow us to maximize the thermal effectiveness, the heat recovery, the design pressure and the pressure drop to suit that application. We work over the whole life cycle of a project, and the aim is to help the system designers optimize that system to get the balance of capital expenditure and operational cost over the project life. And at the end of this, the design output is all the key components are defined, the number of plates that need to go into the core, and the plate channel designs. So there's sort of the key components. So the core's in the middle of it, and everything else is just standard piping components really attached to allow us to get fluids in and out. Mechanical design is to the ASME code. So ASME boiler and pressure vessel code. And there's some references there if anyone's particularly interested to go and look at the guts of that. So I said earlier that, you know, the output was the designer coming up with a definition of the plates to go into the core and the pattern that's on there. So basically we can play with the width, the length, the pattern on there to give us the best combination to meet that thermal and hydraulic performance. And then that becomes chemically etched. So etching's the same process they use for circuit boards, hence the product name. We use ferric chloride to etch stainless steel, and the plates are typically in the range of 1.5, 1.6 up to 2 millimeters thick. And the resulting flow channels have a semicircular cross section with a diameter of roughly 2 millimeters. And the etch plant that we operate is by mass the largest stainless steel etching plant. So once we get those etched plates, they are stacked up and diffusion bonded. Diffusion bonding is kind of the secret of being able to do these high pressures, and it's a solid state joining process. So we don't melt the metal, it doesn't distort and flow like perhaps you'd associate with welding. There's no braze or flux materials in there, it's pure metallic grain growth. And again, that's what's covered within the ASME code is to allow us to do that. And basically those individual plates then fuse together to form the core, which is then has these attachments welded to it. So it's all done to, again, the ASME code, with the welds inspected with either radiography or art and dye penetrant, depending on where they are. Once the vessel's fully assembled, it goes through a code leak test. So we would helium leak test to confirm integrity, pressure test it, hydro test with water to the code requirements. And that's all done with third-party witness to allow us to comply with code. And then once it's all approved, we tidy it up, give it a coat paint, preserve it, pack it, get it ready to go to the client. So I touched on earlier the core markets there, and really today we're going to ignore the first three there for awareness and focus on the power gen. So basically we've been working in this area for a while now. So a lot of the work's done on combined cycle gas turbines, fuel gas heating there to get process optimization, and then waste heat recovery and supercritical CO2 systems. So where you're looking at, heat recovery, secondary cycle power generation for efficiency, and also the energy storage. Say we've got a long history of developing power cycle work. That's going back over 20 years when we started dabbling with the Generation 4 high temperature gas cooled reactors for nuclear work. And that's spawned into the supercritical CO2 power systems, recuperators. We do some work on like the oxy-combustion cycles. And obviously we heard this morning from Johnny, we've been working with HighView, but we're also looking at compressed air, the MAN solutions that Emmanuel mentioned yesterday, for those that were here, and others. So very quickly, there's just some pictures at the bottom there of the units that went to the Pillsworth site. And say we've been working with Highview for over 12 years to support their developments, and we're very excited with where they are right now. This was just a sort of picture of where we are with the oxy-combustion. It's less relevant to today's audience probably, but it gives you a feel for over on the picture up at the top right there, which is the yellow and green heat exchangers that you see on the graphic on the left, how they're kind of lost in the plant size, and the piping kind of almost makes them melt into the background. So in terms of the supercritical carbon dioxide projects, you know, we've been working with that fluid for a very long time, and certainly there's lots of interesting stuff going on. And at the moment we're working as part of one of the H2020 projects that's just about to launch, where we're supporting that project. Just gives you a feel for, you know, the projects that we've been delivering to date. There's an awful lot more work going on in the background in supporting these that you know, hasn't reached the point of hardware being delivered. I think that is it. So it's pretty much on time, I think, there, Adriano.
Absolutely. Thank you very much for your presentation. I think we'll definitely have opportunity later on for picking up a few more details, so we can dive a little bit more in details. But thank you very much for the time being.
No problem.
Thanks. I think we can move to the second presentation before we will let's say address question and answers. So I would like to bring in Professor Brian Emmegard from the DTU Denmark, who will update us and give a talk about the R&D work going on there in his institution. Brian, if you're there, please go ahead. The floor is yours, and share your screen.
Thank you, Adriano. I will try to share my screen.
Yeah.
Do you hear me okay?
See some sort of kind of disturbance when you talk, but let's see how it goes.
Okay, I will try. Otherwise, you should interrupt me if there are any issues. So thank you for this opportunity of presenting some of our considerations and work in task 36 on Carnot batteries. I have prepared this together with Erasmus Rothausen, who is a senior researcher in our department, who is also very much involved in the work in this task in the IEA annex. We are working quite some on heat pumping, and I guess this is why Adriano invited me to talk about this. I will try to cover a bit about what is the state of the art in the field. So first, we already heard different names for the concept, and I just took a short review on Google Scholar of what is available. And as you can see, there are at least these 4 different terms used, and seemingly the first one coming up before Carnot Battery was this thermoelectric energy storage concept, and the publication from which is from ABB is looking quite much like what we are trying to do, at least in some part of the work done in Denmark for the moment, coupling wind power, excess power into thermal storage, and then reaching so high temperature that you could produce steam with a steam turbine and produce power when you have a need for that. some basic considerations leading to the reasoning behind high temperature heat pumps. So this is basically an ideal battery, which is what we're talking about for also for Carnot batteries, that we are aiming at having more or less the same kilowatt hours in and out of the machine, of the machine or of the battery. And due to the storage, we may have different capacity for charging and discharging. In reality, unfortunately, we will not reach 100% efficiency, and so the output will be less than what we put into the battery, and the efficiency for the round trip will be covered by efficiencies related to loss in charging, discharging, and during the storage. For the Carnot battery, this is how we see the technology. So we have a heat pump used for storing. We have or for charging the storage. Then we have a thermal storage at some temperature, and then we have a power cycle that will produce the power. And obviously, we want electric power added to the heat pump. It has a COP, so we will have some temperature input, a low temperature from the source, and we will produce heat to the storage at higher temperature. At some point in time, we will discharge and produce heat from the storage into the power system, and it will afterwards produce power, and it will also have some heat rejection normally. This is a purely theoretical calculation, so we assumed Carnot machines at the temperatures here. So for 250 degrees Celsius in the storage and an ambient of 25, adding 1 megawatt hour would give a COP for Carnot machine of 2.3 for storing, and an efficiency of 43% for producing. And the net output would be that we would have the same output, 1 megawatt hour, coming out of the turbine as electric power. So this could be one option, but we could also select other temperatures. For example, we could have higher temperatures like the one shown before, which has 700, or here 500. And the cost of higher temperature would be that we would have lower COP for the heat pump. So in this case, 1.6 still for Carnot machine, and we would have a higher efficiency when producing power of 61%. Multiplying these two values once again would give us a 100% efficient battery. So we can have different temperatures. We could also say, what about lower temperature? That would make it easier to find the heat pump. So for example, what about 50? Then we would have a very high COP with a very low lift in the heat pump, so 13. But the power cycle would only have an efficiency, if it were a Carnot cycle, of 8%. Still, multiplying these two values would give a 100% efficient battery. So from a theoretical viewpoint, we don't need high temperature in the storage. We could basically aim at whatever temperature would be most appropriate for the available technology. However, the machines would not be theoretical. So for example, if we now take the 250 degrees machine and we assume that we have a cycle for the heat pump and for the power cycle that would reach 80% of the Carnot limit. And that may still seem a bit high, but we could see if we would probably have some temperature glide, and then we should compare to the lower cycle, which would have a little lower efficiency. So I would not say that 80% is completely unreachable, but still is fairly ambitious. In this case, we would have 1.9 as COP, and we would have 34% production efficiency for power, and that would reach a 64% round trip efficiency of the system. So we need efficient machines. We need to get close to the Carnot cycle, which is also what was shown earlier today and stated about the idea with the exergy application. So this is one kind of loss in these machines. Another loss would be due to temperature difference. When we want to transfer heat from the ambient into the heat pump, and when we want to transfer heat from the heat pump into the storage, and from the storage back into the power cycle, and also afterwards rejecting heat from the power cycle to the ambient, then we will have a temperature difference. This will also cause exergy loss and will decrease the COP to 2.2 and the efficiency to 40%. And in this case, we would have 87% round trip efficiency. In reality, we would obviously both have losses in the cycles and also due to temperature differences. So an assumed system that could probably be realized today, even if it seems to be ambitious to be able to reach this efficiency of 80%, and perhaps also the low temperature differences of only 10 Kelvin. We would have a heat pump with a COP of 1.7. We would have an efficiency in the power production of 32%, and we did discuss this value if it would actually be possible to reach 32% with 250 degrees inlet. I don't think it's available on the market, but we might hope that someone could provide this. Because this would make us have an efficiency, round-trip efficiency of the system as a battery of 56%. And obviously, in order to be competitive or feasible, then the electricity price has to go the opposite way. So we would have a requirement for more or less 2 times selling price compared to what electricity costs when buying in order to have a feasible operation. And well, there are many electricity storage technologies that are considered for the Danish case. This is one, but we would have this requirement in order to reach a feasible operation, even if we have fluctuating wind power. But another competition that we also have to consider is using electricity for power to X, which would probably give a product with higher price, or using it for district heating production. We have the district heating grids that could consume quite much power in an efficient way with heat pumps alone. So far we don't have any Carnot battery in operation, and it doesn't seem to be completely feasible in the system today. This is part of what we will study in our part of the task in the IEA project. So a bit more about the work that we are also doing on high temperature heat pumps. This is one of the analyses we've made. So a cascade cycle with a hydrocarbon system for obtaining, for retrieving the excess heat from the industrial plant and then producing steam at different temperature levels. This is a case for alumina production, and it's obviously not something that has been realized, but has been calculated. What we found were a COP of 1.9 in total for this system, which would be a Lorentz efficiency of 50% compared to theoretical limits. Looking into net present value for different locations and using 2020 prices, this would not be feasible for the Danish case. It would, however, be feasible in Norway and for Germany. So high temperature heat pumps seem to be have some potential outside Denmark, where we couldn't really compete with natural gas. Another system from the same study was a reverse Brayton cycle with CO2, so high temperature or high supercritical CO2. This would reach a COP of 1.7 and a little lower Lorentz efficiency. And in this case, what we found were that it was not feasible for Denmark or Germany. It would be feasible and have a positive net present value for Norway. I would also like to mention some of the other work done, and this is not really for high temperature heat pumps, but we have been investigating options for using mixtures, zeotropic mixtures, to match temperature glide in source and sink by the working fluid. And what we found here, obviously you can see the working fluid compositions, and there are many more, but those that have positive improvement by using the zeotropic mixtures are shown on the right. What you see is that, for example, the blue one for the pure fluid, we would have a COP of 4 for any of the 2 pure fluids. But if we do the mixture in the right way, we could reach a COP of 4.5, so 10-20% efficiency improvement for these different mixtures, and those were based on natural working fluids. And you can see there are several options for improvement by using these zootropic mixtures, and we are doing some work in this field. If you look into the literature, one of the very comprehensive reviews made is this one from the guys in Switzerland. And talking about high temperature heat pump, obviously we need some definitions, and their definition is that a high temperature heat pump would reach over 80 centigrade. So this is quite far from the 250 I had in my calculation. And a very high temperature would reach between 100 and 160 based on what is available on the market today. So we are still somewhere, somewhere we still have some way to go in order to reach the demand that could be needed for Carnot batteries. And this is then the overview coming out of this review paper. As you can see, there are capacities reaching from less than 100 kilowatts and up to several megawatts. It is different types of machines, and they reach from 90 degrees Celsius degrees and upwards, and some of them would be able to reach 150, 160. As far as I am aware, this second one, the Viking heat booster, is no longer active in the market, unfortunately. So this is more or less what is available. Then there are technologies that are coming. One is this one from Norway, the Olvondo technologies. It's a Stirling cycle. They do have machines in operation for high temperature for steam production, in this case in industry, reaching 180 degrees, 500 kilowatt capacity, and a COP of more or less 1.4, 1.3, 1.5, something like that. They do have a few machines in operation. They have several thousand operating hours in total on these machines. So technology is on the way for reaching the higher temperatures that might be needed in order to reach sufficient efficiency in Carnot batteries using these kinds of storage technology. Then I would also like to mention that we have recently started this project funded by the Danish Energy Agency. As you can see, the fluids are water, it's CO2, and it is hydrocarbons. So again, we have a focus on natural working fluids. We have a number of case studies, and we have a number of providers that will be involved in the project. And what we are aiming at is reaching heat pumps that would provide the demand for industry of up to 200 degrees Celsius for industrial heat production. Maybe hopefully we will be able to also come up with technology that would be available for electricity storage. So coming to the end, I have focused on Carnot batteries for storage of electricity. There are many options for heat storage which you would have to be able to compete with. It's a hard competition. And it's also an observation, at least for Denmark, that bulk electricity storage is only to limited extent feasible today. And it is not that we have large scale electricity storage in place. So this work is very much for future need when we have much less fuel available in the system and only have at some point wind power and solar power, for example. We need, in order to use a Carnot battery or any battery, we need to decrease the losses for charge, for discharge, and for the storage. and that would involve high cycle efficiency requirements, and it would probably also require low temperature differences between the parts of the system when doing the heat transfer. For high temperature heat pumps, there are a number of solutions available. We have most focus on natural working fluids, and it is interesting to see that there are actually quite a number of solutions that are being presented for the moment for market conditions or close to market conditions. This is positive for the Carnot batteries probably also. And since this focus is mostly on high temperature heat pump, I just want to show the front page of a white paper we wrote together with a number of European collaborators on high temperature heat pumps and focusing on that. And I can definitely provide that if anyone would be interested in reading more about this work. Thank you.
Thank you very much, Brian. That's, I think, a very interesting talk, and that'll probably open up quite a few questions and needs for further development in this space. So we have certainly time for questions. So obviously, if anyone is interested in dropping the questions in the chat box or in the Zoom facilities, I'm more than happy to do so. So I think Yulong, you have both a thumb up and a hand up. So maybe you have a round of questions.
Thank you, Rach and Adrian. I always just try to open the questions, but I mean, first of all, thank you, Colin and Brian, for the presentation. I think this is an area which is actually I see as a highly challenging area particularly for high temperature heat pumps. And I mean, the aspiration is to have the heat pumps which can pump the heat to about 400 to 600 degrees C. If that, so, so Brian, if I come back to go to you first, and then I know from Colin, the heat changer side is no problem with pressure or temperature, to go to 6 or 7, even 800 degrees C. And from the heat pump itself, mechanical aspects, what would be the main sort of challenges, and what would sort of the likely COP for if we want to pump the heat to 400 degrees C, for example? So just be interesting to know your view on that.
Yes, unfortunately, I don't think that we should consider or be very optimistic about which COP would be able to reach, because we are limited by the Carnot cycle. So it would be very hard to reach very high COP of a heat pump. And that would probably be the main limitation for using heat pumps. This Olvondo Technologies, which is probably the one that reaches the highest temperature for the moment, and that is reaching a COP of 1.5, could probably reach higher, but it would definitely be less than 2. And that is still better than just heating by electric resistance. If it is 400, 500, 600, then I would. It should definitely be considered whether it's worth to use a heat pump, or it should just be electric heating. There could be options by gas cycles. So that is one way to do it.
Yes, understood. So Brian, if I sort of ask further, the question is, so tactically, is that possible, or just is cost perspective is not sort of worthwhile to do that, or the technically, the COP decreasing with temperature clearly from what you just mentioned, and but 200 degrees C you can probably by 1.5 after 2, I think realistically. So if we go above 200 and probably is rapidly approaching 1, which is probably just doing resistive heating. Is that what you imply, or if you could elaborate that just from expert point of view?
At some temperature, it would no longer make sense to try to reach to try to implement a heat pump. They would be more expensive investment-wise. But there are technologies coming or being investigated for 500-600 degrees, and the technology is possible to make. It is more a matter of what has been a market demand so far. I think that has limited this potential. Okay, understood. Thank you very much. And then I'll stop. Sorry.
Thank you very much for the questions, Yulong. So we have just a couple of questions. Certainly, maybe a comment for Brian as well. There is some interest in the document you mentioned in your last slide, so probably worth to share it if possible. Probably I picked the question for Colin about if Heatrick develops also, let's say, heat exchanger for very high temperature, like a ceramic heat exchanger for applications above 1000 degrees C or so.
Yeah, so the simple answer is not yet. At the minute, we've stuck with metals, so high temperature alloys. We've looked at some feasibility studies for stuff like silicon carbide, but we haven't progressed it very far at the moment, purely because there's not a great pull from the market yet. So at the minute, the likes of the net power projects that I've flashed up at the end, that's going hot and high pressure and using some ink alloys, but it's all within the ASME code. And yeah, at the minute, most people are choosing to get stuff that's readily available with a bit of industrial track record. So yeah, we're serving that, but keeping an eye on what might come next.
Okay, thank you very much. Perhaps I'll add a question here from my side on the actually other end of the spectrum from temperature applications. So you mentioned or you presented your chart with let's say maximum pressure versus operating temperature, I guess for actually temperature above room temperature. Is any challenge or any specific aspects that was necessary to take into account for applications like for liquid energy storage, so relatively high pressure but cryogenic temperatures?
So I mean the combination of temperatures and pressures, it's more around understanding the operator's need. So where the sort of startup time over the temperature spans, looking at the mechanical stresses that might come from that. But from we've been working in the LNG industry down at the sort of minus 160s for a long time. So we've got a decent amount of experience in looking at what comes there. And then it's just looking at what's needed. But there aren't the same level of restrictions with our type of equipment that you see with some others, which is how we got into the LNG industry in the first place. So it's looked at on a case by case to understand what the operating requirements are and what considerations might come from that. But there's no hard limitations that we've run into really.
Okay, thank you very much. Looking at if there are any further questions in the chat or anyone with the hands up. Perhaps they've taken the opportunity again for a question for you, Colin, around the, let's say, applications of the Heatrick, let's say, components. So you mentioned in one of your slides, you're looking at also thermal storage or thermal energy storage developments. was aware that there is some perhaps confidentiality aspects mentioned in your slide, but can you expand a little bit more in what potentially you're looking in the domain of thermal energy storage from ITRIC perspective?
But it's all around the efficiency and the heat recovery type stuff. So there's a few different systems. What we're looking at is who needs the operating parameters that others can't offer, if you like. Clearly, there are other technologies in the marketplace that are possibly more of a commodity item, less bespoke, and that gives you an advantage in terms of availability and price point. But when you're trying to push the edges of the envelope, that's where we're coming in, and it's difficult really to say much more than it's the heat recovery and efficiency stuff.
Okay, well, thank you very much. So see if there are other questions. So if you have any questions, please drop them in the chat. Otherwise, I'll take the opportunity to ask a couple of questions to Brian as well. So interesting to hear a little bit more around the let's say market constraints for the applications of either, let's say, Carnot batteries or eventually the high temperature heat pumps. It sounded to me from your presentation that there are some specific constraints that might make the Danish environment or market more challenging than others. You mentioned that some of the technology you are looking at were feasible from economic perspective, let's say in Germany, not in Denmark. What are the specific constraints from Danish market perspective that makes the application less favorable from an economic perspective?
The main concern in this case, that was the difference between natural gas price and electricity price for the moment. And natural gas price or electricity prices were so much higher compared to the natural gas prices for the industrial application that it didn't seem feasible for the moment. That will obviously change in future, where natural gas, fossil fuels will be no longer available at some point, and biogas or other gases would have significantly higher price. So the high temperature heat pumps will find a much bigger market share, and this is happening for the moment, surely.
Okay, thank you very much. See if there are any let's say final questions from the attendees. Any final burning questions here? Doesn't seem so. So,
Adriano, there's one more question concerning the organization from Hugh Gross. He wants to know if, when, and probably how we are going to share the videos and the presentations.
Yes, that's absolutely good question. So we'll let's say check the recordings from Zoom facilities, and we will make available the let's say the presentations if speakers are happy to share them through let's say the channels that were involved in this in the organization of this webinar. So the Supergen network website, obviously from the DLR side, if you are happy to share through the let's say your website, and the let's say community around the IEA task 36. And Angela, you can correct me if I'm wrong. We will, if the attendees and presenters are happy with it, can also have the videos on, let's say, social medias or YouTube. Angela, can you just give a quick feedback if that's the case? Yes, I see a thumb up. Okay, so that's let's say how will the material will be made available. Hopefully, it's satisfactory for everybody, and we'll also request again to the speakers today and yesterday if they are happy to share the presentation, so we can also upload those one on our websites. Okay, so I don't see any other questions here, so I think we can wrap up, unless Dan, you have other questions on this aspect.
No more questions.
Okay. So perhaps I'll take the opportunity, obviously, to thanks everybody for attending, and the presenters to commit their time to this event. As mentioned, the content of this webinar will be made available if everybody's happy with it. I would like also to mention that the IA Task 36 is organizing, let's say meeting for the whole task in April, and some of you might have received already the save the date invitation. So we'll certainly circulate and make people aware of this event, and you are obviously welcome to attend also this meeting around April. So that's all from our side. So thank you very much again, and hopefully we will meet soon also physically in the future events of the task and around research in Carnot batteries. So thank you very much, everybody, and thanks also all the other people involved in delivering this webinar and make it a successful event.
Thank you, Adriano, for chairing this webinar in that way. Thank you really very much. I think it was a really not only interesting webinar, but we really got a wealth of information. So thanks to all the presenters as well. This was really, to my opinion, well organized and a webinar with, as I said, a wealth of information. And I would also like to thank the organization team. Angela, thank you to you as well. So I'm really happy to have these kinds of webinar, and hopefully we are able in the future to have more of them, also in other countries, maybe one in Asia, to have input also from experts from there.
Okay, fantastic. Thank you, Dan, and thank you everybody, and have a nice weekend as well. Bye bye.
Everyone. Thank you. Bye.